Good morning, everyone. Today, your Friday assignment is going to be just some practice of using the equations that we talked about Wednesday and Thursday. All right, so we took some time Wednesday and Thursday to build these kinematic equations. All right, and I know at first they kind of seem a little bit strange and they can kind of seem like there's just a lot of variables to remember. We're going to practice a bunch of them. All right, and by the end of this, hopefully, we're feeling a little bit more comfortable with the idea of how we approach problems that involve motion and how we use our kinematic equations. All right. So what I'm going to do is I'm going to kind of guide us through the first couple questions. And then I'm going to want you to kind of actually just work through them yourself and then periodically come back, kind of check the answers, that sort of thing. So let's start with the very first question. All right. So it says the required takeoff speed for a certain airplane is 100 meters per second. And this has multiple parts. The first one, it says if the plane starts from rest at one end of a 1 kilometer long runway, what acceleration is necessary for the plane to reach this takeoff speed? Now, again, these are the type of questions you're going to run into when we talk about motion. Things that involve displacements, accelerations, velocities. All right, these are all going to be very important to kinematics. And in order to organize our thoughts, we need to do the thing that we always do when we talk about kinematics, which is we start by drawing a kinematics chart. All right. Now, you can notice I've already to the left, I've drawn my kinematics chart and I've filled in a couple of things. Remember, it doesn't matter what order you put these in, just as long as you have all 5 variables. So I've got final velocity, initial velocity, acceleration, time, and displacement. All right. Now, we're going to make a couple assumptions about this question. All right. One of the main ones we're going to make is that we're going to say that it's going to travel the whole runway before it takes off. All right. Now, of course, in reality, a plane usually takes off before it gets to the end of the runway. But in this case, that'll be an assumption we make. All right. So with that being said, we have a couple pieces of information we can put in our chart. First, it says the plane starts from rest. So right away, that tells me, oh, my starting velocity is 0. Because again, when things start from rest, they start with a velocity of 0. So VI is 0. Next, it says, what's the takeoff speed? Again, the takeoff speed in this case, it doesn't explicitly say it's the final velocity, but you can kind of assume this is going to be the end of when we're looking at this. So because of that, that means that the takeoff speed, which is going to be the final velocity, is just going to be 100 meters per second, because that's what it tells us in the problem as well. All right, so right away we now know 2 pieces of information. We know VI and we know VF. All right. Now remember, we have to have at least 3 pieces of information about the motion of an object in order to use kinematics effectively. So looking at the other things, doesn't tell us acceleration, but we're looking for that, so hold on to that one. Time doesn't tell us anything about the time. Delta X, displacement, it does tell us. It tells us how long the runway is, all right? And which means that we're going to make the assumption it's going the whole length of the runway before it takes off. So because of that, we're going to say the displacement is 1,000 meters. Now again, this kind of goes back to this idea we talked about with base units, all right? When we're talking about motion, kind of our main goal is we usually want to go back to meters if we can. All right. So if you solve this question and you left it as 1 kilometer, your answer is going to be off by a factor of about 1,000 because it's going to be using kilometers and combining it with meters, which is going to cause some issues. All right. So we know 3 pieces of information: VF, VI, delta X. We want to find A, which means we need to pick the only equation we have that doesn't involve time. All right. Now, going through the 4 equations that we have, you'll notice that the one that does not have time would be, I'd call it the last equation. It would be the last equation we came up with in our notes. And it's this equation that says the displacement of an object is equal to the final velocity squared minus the initial velocity squared divided by 2a. Now again, in case you want to know how I actually got that, you're welcome to come to office hours. I'm happy to kind of show you the math of how we create this formula. Because it's just a couple of math tricks we use to come up with this. But what's important is that, again, we know all the pieces of information that we have here to figure out what we're looking for. All right, so I start by writing the equation. Then, the way I did it is I got rid of the VI because it's 0. Probably the easiest way, honestly, to do this is before you do anything else, just move the equation around so you can get A by itself. All right, now, that's pretty simple because if you're just doing a little bit of algebra, you want to divide both sides by x, multiply both sides by a, and you'll get that now acceleration is going to be equal to VF squared minus VI squared divided by 2 delta x. All right, and that's kind of what this formula is over here, just simplified because the VI squared is 0. All right, now once you do all that, boom, we know all three of these things. All right, we know what VF is. It's 100. So where the VF is, put 100. Delta x is 1,000. So right there in the bottom, we put 1,000. All right, then it just comes down to squaring everything. All right, so you're doing 100 squared, which is 10,000, times 2 times 1,000, which is 2,000, which means once you solve for everything together, the acceleration is just going to be equal to 5 meters per second squared. All right, and that's basically the minimum. If we're kind of talking about like ranges and things like that, that's the minimum acceleration. That's the absolute lowest amount of acceleration this plane can have and still successfully take off. All right, so in a way, that's kind of what we're trying to solve for here by saying that it goes the entire length of the runway. This is the absolute minimum, the lowest safety threshold it can have and still make it safely. All right, now the next piece. This is something we haven't really talked about in this class, but this is actually a very important piece of a lot of different things in AP Physics 1, especially a lot of things in the AP exam. It's referred to as something called proportional reasoning. All right. Now, proportional reasoning is basically a fancy way of saying only use variables. All right. And what it does is we basically come up with a formula, just a basic one, and then we change one thing in that formula and see how it changes everything else. Right? So let me kind of explain. So it says the planes accelerate from rest at double the rate found in part A. How would this affect the plane's takeoff speed at the end of the runway? All right. So basically, if it went the whole way, all right, if it kept accelerating at now twice the rate and it was going down the whole runway, what would that do to the final velocity now? All right. Well, what you could do is you could just literally use kinematics and you could solve for it using numbers, kind of like we did up here, and then figure out how it affects VF. And if you want to do that, that would be totally fine. However, there's a more effective way to do this that gives it that you could figure out the ratio no matter what. Without, all you would have to do is literally just put in a final velocity. All right, so proportional reasoning looks like this. You start by drawing a kinematics chart. Then all you do is you basically put in variables. So you basically don't change anything. You just leave it as a variable. The only thing you can change is anything that's equal to 0. So VI is 0. Again, I don't know anything about time, so I'm just going to leave it like this and put it right back to that same formula we used before. So what I do now is I solve for VF. I solve for this formula. All right, because at the end of the day, I'm trying to figure out how fast the plane's going at the end of all this. So I'm trying to find VF. So I do a little bit of algebra. Again, at this point, this is something, if you're not comfortable doing the algebra, please, you need to come to me during office hours because this is something we need to practice so that we are very confident with it by the time we get to kind of the quiz for kinematics. All right. So I do that. I move some stuff around. I solve for VF squared, and I get that VF, the final velocity of anything, is just equal to the square root of 2 times acceleration times delta x. All right. Now, this is where the proportional reasoning part comes in. We want to find the new final velocity. All right, so this would be considered kind of the original final velocity. This is, and if I plugged everything in from this question, I would get 100, all right, meters per second. Now, what I'm going to do is I'm going to rewrite this. I put this little dash here to represent this is VF prime. This is new final velocity. And what I'm going to say is I'm going to say this is this formula, but I'm going to change the acceleration to now be 2 times the original acceleration. So the new VF squared, the new VF is equal to the square root of 2 times the new acceleration, which is 2 times a, times the same delta x. It's going to go the same distance. All right. Now, again, this can be a little confusing math-wise, but it's just kind of doing a little bit of math tricks because I can take out, what I'm actually going to do is I take out the square root of 2. So remember, everything under this square root, you can kind of break it up, and it's the equivalent of everything being said. This is the square root of 2 times the square root of 2a times the square root of delta x when everything is under the square root. All right? Well, I pull out the square root of 2 because if I leave everything else under that other radical, that square root of 2a delta x, you'll notice this is familiar. We've written this before. This is actually the formula for the original final velocity, how we calculated it. All right? So I can actually do a little substitution, and I can put this final velocity back into this new equation. All right? And because of that, what ends up happening is I get that the final velocity, the new one, if I have double the acceleration, is actually going to be the square root of 2 times the old final velocity. All right? Now, if you don't believe me or you're like, oh, I really hate this algebra, okay, then go through and I want you to test it. Because what you should be getting is that the new final velocity is 141 meters per second, which is going to be 100 times the square root of 2. All right? So if you want to test this one out, go through, solve for it using the numbers, the new ones, and see if that's what you get. All right? Now, that's one way to use proportional reasoning. We have another one as well. This one says that the plane accelerated at the rate found in part B. So now it's got the new acceleration again. What distance would it cover before reaching its required takeoff speed? Now this is an interesting one because it's slightly asking this question in a different way. All right? Because what it's basically saying is it wants to know what would the distance now be? How far would it go, that displacement, before it reaches 100 meters per second? All right? Now again, proportional reasoning. What this tells me is that I first start by writing everything as a variable and putting anything as a 0 if it needs to be. All right? This time again, once I do that, proportional reasoning says I need to come up with this a general formula. So I take that delta x, we're using the same formula again, delta x, vf squared minus vi squared over 2a. All right? Reduce, I get rid of the vi squared because it's equal to 0. And then I just rewrite, I kind of leave it like that. So that's the general, that's how we would solve for how far it goes, its displacement. Now, for the next part, we do the same thing. We rewrite it as this new displacement, delta x prime. All right, equals the same, it's going to reach the same final velocity as it did originally, so we're not changing that. But the acceleration is now double what it was originally, so I replace that a with 2a. Then, I kind of do the same thing I just did above. I look to see if I can kind of pull something out so that the rest of the equation looks similar. So, if I pull 1/2 away from everything, all right, and it becomes 1/2 times vf squared over 2a. Well, that vf squared over 2a is what we calculated originally as the original distance. All right? So if I substitute that in, I get rid of that, I put in delta x, I get that the new distance, how far it goes down the runway, is only half the original distance. So originally we said it was 1,000 meters. This says it's only going to be 500 meters. And again, if you want to, if you're like, I don't really believe you, I don't really get this, do it with numbers and prove that. All right, because you should see that it should be half the original distance or half the distance of the runway. All right, and again, proportional reasoning is something that can be very confusing at first, but it follows the same general rules as everything else we talked about in here. You kind of you basically write down the formula, you plug in the stuff for it, and then you kind of see what happens when you change one thing and how that affects the rest of the formula. All right, so with that being said, all right, let's kind of go through this next one. And then the rest are going to be kind of up to you to do. Second question. A sports car can go from 0 to 40 meters per second over a distance of 100 meters. What is the acceleration of this car? All right. Well, at this point, we should start getting very comfortable that the very first thing we need to write down is a kinematics chart. We need to fill it out. All right. So again, we think about what's in our kinematics chart: initial velocity, final velocity, acceleration, time, displacement. Well, looking at those different things, all right, we actually can fill out a couple of those. All right, we know what the initial velocity is because again, it says it starts at 0, so it rests. So vi is 0. Vf, 40 meters per second, because that's how fast. That's kind of the end of when we're looking at it. So Vf is 40 meters per second over a distance of 100 meters. Now, this has been a little confusing, and I understand because I keep saying displacement, and it's the questions are saying distance. When we're going in just one direction, which is basically all these questions are, distance and displacement are actually the same thing. All right, so when we haven't changed direction, we're just going in one direction, which is what we're doing right now with kinematics, then our displacement and distance are going to be the same. All right, so we can use it interchangeably, which means that in our chart, delta x is going to be 100 meters. All right, well, again, wants to find acceleration. So we ask ourselves, what 3 things do we know? Vf, Vi, and delta x. What do we not know? A, which means we want the equation that has those 4 things in it, which again, the equation that has those four things is that fourth equation in your notes. Delta x equals vf squared minus vi squared divided by 2a. So, because of that, you need to do a little bit of manipulation, move some stuff around to get a by itself. Once you do that, you just plug in what you know into the equation, which is exactly what we did. Solve for acceleration, boom, 8 meters per second squared. All right, and again, it seems like it can be complicated and it can be confusing to kind of set up that stuff at first, but I promise, once you get comfortable, once you write down all that information that you know in the table, it just comes down to picking the equation and plugging it in correctly. All right, so the acceleration, 8 meters per second squared. And if we want to, you can actually, I would add it to your chart because it just gives you another piece of information that you can kind of go with. Because at the end of the day, we pretty much always want to fill out our chart. It's kind of the main goal here. All right. Now next is how much time does it take to cover this distance? All right. Right there, you kind of can use you can use just about anything, all right, to solve for this. So any of the equations that have time, you're welcome to pick and solve for it based off of what we have. I used the first equation, I believe, that we came up with in our notes. And again, I plug in what I know. VF is 40 meters per second. VI is 0. Acceleration 8 meters per second squared. Do a little bit of math. And I solve for time, and the time is 5 seconds. All right? So, it's been moving for 5 seconds. And the next piece, I want you to try and work through. So it says, how fast would the sports car be moving if it kept accelerating at this same rate for an additional 3 seconds? All right? And there's a couple ways to do it. One, you could calculate how you could basically maybe look at the time from 6 seconds to 8 seconds if you wanted to do that. You could rewrite the chart and you could basically say, kind of reestablish what we know. All right, we could say again, oh, I know VI is 0. I can this time say, I know that time is going to be 8 seconds because that's what we're asking. How long has it gone, basically, if it's accelerated for 8 total seconds. And I know the acceleration. All right, but I want you to go through and try it out. Try to figure out how to solve for it, and then we'll discuss. And feel free to pause the video if you kind of want to have some time to work on it. All right, because for this one, all right, there's a couple ways we can do it. The way I did it is I rewrote my chart, all right, and I changed up some of the things that I knew, all right, because actually now that I've increased the time, a couple things have changed, all right. So because of that, I don't actually know the final velocity anymore because it's not 5 seconds anymore. So I'm looking for that. So, it's important. I do know the starting velocity. It's still 0 because we're still starting from the same time. I know the acceleration now because I solved for it earlier. It's 8 meters per second squared. And I know the time, which is 8 seconds, because it tells me that it's accelerating at the same rate for an additional 3 seconds. So it's been allowed to go for 8 total seconds. This is also why I can't use the delta x from originally, because that was only for a 5-second interval. This is an 8-second interval. All right? Once you do that, pick the equation that you want. What equation has VF, VI, A, and T in it? It's going to be the first equation. All right? You want to find VF, plug in everything else. VI is 0. Acceleration is 8 meters per second squared. Time is 8 seconds. The final velocity here in this case is going to be 64 meters per second. All right? And again, always start by drawing your chart. Always write down what we know. You must have 3 things in order to solve for any of the other ones. All right? And I promise, you're either going to, as we start to go through this, you're going to start to see that motion builds on itself. So you might be pulling information from different parts of questions that we give or different things that you've learned that might be important to the motion of an object. All right? So, at this point, for question 3, I'm just going to I want you to pause the video. I want you to take as much time as you need to answer those questions, and then we'll kind of review them. All right, but at this point, it's going to be less guided practice and more I'm giving you the chance to work through it, and I'm just going to I'll kind of review the answers quickly. So pause the video, take as much time as you need to, and when you're ready, unpause it, and we'll talk about it. The one thing I will say is make sure that you acknowledge that it says over the course of 2 minutes and that you might need to turn that into something else. All right. So hopefully you had a chance to kind of work through this question. So the first one, what distance does a train cover during this time? So remember, because this thing is moving in one direction, distance and displacement are going to be the same. Now, first thing we do, fill out a kinematics chart. All right, and oh my gosh, I actually don't have one. I have it down here. But kinematics chart, the final velocity. This one looks a little bit different. All right, the final velocity is actually 20 meters per second because that's how fast it's going when we stop kind of looking at it. Initial velocity, 50 meters per second. All right, because it's slowing down. So you're gonna remember you can have a starting velocity be going faster than an end velocity if you're slowing down. All right. I also know the time as well. It says 2 minutes. But if you left it as 2 minutes, you're going to get an answer that's incorrect because you need to actually turn it into seconds. The 2 minutes is 120 seconds. So once you do that, you pick the equation that has all these things in it. It's got VF, it's got VI, it's got T, it's got delta X. I actually did this I did this a little bit differently. I went out of order when I answered my two questions. The formula you're going to want to use is going to be the second formula based off of what you know. All right, because according to the second formula, that on your notes, that has delta X, T, VI, and VF. All right, but in either case, you're going to get the same answer, which is a displacement of 4,200 meters. All right. Next, it says, what is the train's acceleration during this time? Well, again, I already have 3 pieces of information, so I can solve for everything else. So I'm looking for the formula that has VF, VI, A, and T in it. Boom. That's going to be the first formula. I go through, solve for acceleration, and I get that it's actually going to be negative. It's negative 0.25 meters per second squared. All right. And that makes sense. It should be negative because we're adding negative velocity every second, which is why it's slowing down. All right. And as we start to kind of go through this, we're going to talk about in the next couple of weeks the idea of why acceleration might be negative if my velocity is positive, because it's going to have to go back to the idea of forces and which way a net force points to slow something down. All right. Next, it says if the train continued to slow down at the same rate, how much more time would it take to come to a complete stop? All right. Well, again, you know the acceleration. So what you can do if you want is you can kind of you can write your chart, a new one, and you can kind of change it up a couple ways. You could either, one, start the VI, and you could just say, all right, I'm going to say VI is 50 meters per second, and then indeed VAF is going to be 0, and write down the acceleration. You could also do what I did, which is I just basically looked at the idea of, well, I just want to look at the time frame from when it's at 20 meters per second to when it stops. So I say the initial velocity is now 20 meters per second because I'm like looking at a new time frame. The final velocity is going to be 0 because that's when it stopped. The acceleration is still the same as before, and I'm looking for time. And again, I look for which things I know, VI, VF, A. I don't know T. The only equation that has those 4 things is the first one. All right. And going through, plugging in all that stuff, you get that it's going to go for 80 more seconds. All right. Now, if you did it the other way where you said VI was 50 meters per second, VF was 0, and the acceleration was negative 0.25 meters per second squared, you would probably get an answer of 200 seconds, which is the total time and for all of it that it took to slow down. But remember, this was asking how much more time would it take past the 2 minutes that we looked at. All right. Nice. All right. Next question. A driver starting from rest accelerates at a rate of 2 meters per second squared for 15 seconds until reaching a certain speed. She then continues driving at this constant speed for an additional 15 seconds. All right. Now, this is just one thing I want to point out before you do this, and this is important with kinematics. Kinematics is useful in many ways, but it has one very, very important flaw, and that is it only works if the acceleration does not change over the time you're looking at the object. If the acceleration changes, you have to draw a new kinematics chart. All right. So anytime the acceleration of the object changes, you must draw a new kinematics chart and look at that motion. All right. Well, this question is no different because it says it accelerates at a rate of 2 meters per second squared for 15 seconds. So you can draw a kinematics chart for the first 15 seconds. All right. But then it says this driver continues driving at a constant speed, which means that now the acceleration has changed. So you're going to have to draw a new kinematics chart for the last 15 seconds. And I promise, you can still do kinematics even if the acceleration is 0. It just kind of makes it a little trivial, or you're kind of limited in what formulas you can use. But I want you to figure that one out. All right, so if you could, go through, solve these questions. The one thing you don't have to do is don't answer part B. All right, so really, you're just doing part A. Part B, you don't need to worry about because it's kind of a weird question. and it's not that important to what we're talking about. So pause the video, work through it. Once you think you got it, unpause it, we'll discuss. All right, so going right through here. Again, I told you, you need to draw two charts. All right, first part, the chart for the first part, first 15 seconds, starting velocity is 0 because it starts from rest. Acceleration is 2 meters per second squared because it tells us in the question. And it's going for 15 seconds. All right, so because of that, I know three things. I want the fourth. In this case, I want to find delta x. So I'm going to use the third equation because that is the equation that has delta x, vi, t, and acceleration in it. Plug in everything that I know, solve for it, and you get that for over the first 15 seconds, our car travels 225 meters. All right, but that's not the final answer because it also goes for another 15 seconds. But this time, it goes at whatever velocity it is now at. All right, once it stops accelerating. Now, I didn't actually write down the formula to do this because I just kind of did it in my head. But it's a very quick calculation. All right. Because all you need to do is you need to remember how acceleration, time, and velocity work. Remember, velocity is just acceleration times time. All right? So because of that, to figure out how fast it was going, I just basically said, all right, well, the acceleration is 2 meters per second. It goes for 15 seconds. So that means every second the driver gains 2 meters per second of velocity. So because of that, after 15 seconds, the driver is moving at 30 meters per second. All right. Now for the second part, the new chart we have to draw. It seems a little trivial at first because VI is 30 meters per second. Well, VF is the same thing, also 30 meters per second, and that's not a problem. You can definitely write it down that way because that's perfectly acceptable for kinematics. Acceleration is now 0 because it's constant speed, and the time is another 15 seconds. All right. Now because of this, you actually run into you can only use a few equations when you have a constant speed. And in fact, really the only equation you can use is actually going to be this equation right here, the delta x. And really, they all kind of reduce to the same thing when the acceleration is 0. But what you'll get is that basically delta x is going to be the starting velocity. It's going to be the velocity that it's traveling at times time. And again, that's also an equation we've seen before when we talk about constant speed. So it moves at 30 meters per second for 15 seconds. Which means multiply them together, and you get then in the second section, it moves forward with 450 meters. So, to get the total distance, you just add the first one to the second one. Once you do all that, it's 675 meters. All right, so, again, it can seem kind of confusing, but again, you always go back to the same idea. You start by drawing a chart, and every time the acceleration changes, you draw another chart. All right, and you do that until you have found everything you want to know about that object. All right, last question. Again, driver moves at 36 meters per second, then brakes hard, coming to a stop over a distance of 45 meters. All right, at this point, I want you to go through, work all of it, and then we'll just kind of review. When you're ready, so pause the video, and then when you're ready, unpause it, and I'll talk about the answers. All right, so here are our answers. How much time does it take the driver to come to a stop? I got 2.5 seconds. Again, I start by drawing my chart. At this point, I think it's pretty clear. You can kind of see where I'm getting all this information from. The main thing is that the reason I know VF is 0 because it says it comes to a stop. What's the acceleration during this braking? Go through, do all the math, plug in correctly. The acceleration should be negative 14.4 meters per second squared. And then the last question, is the driver's acceleration directed to the left or the right, or can this not be determined? And the actual answer is that some of us might want to say if the acceleration is negative, like, oh, it's going to the left, because we like to define positives to the right, and that's fair, but we haven't actually explicitly said anything in this question about what is positive or negative. So in fact, you can't determine which way the driver is accelerating, all right? I don't know if they're accelerating to the left or to the right. It doesn't say in the question, all right? So right there, I know this is kind of a longer video. I know it seems like we kind of went through a lot of questions, but they're all the same process. I look at the question. I write down the kinematics chart. I write down the information that it gives me, and then I use that information to solve for what I want to find. All right? So, with that being said, that kind of finishes this video, finishes these notes. You do have homework as well. Homework, I want to say, I think it's OB11. It's just kinematics review. All right? And a little bit of graphing review as well. So next week we're going to go back into forces. We're going to start tying kinematics and forces together. So we're going to start seeing them hand in hand. So if you have any questions, please don't hesitate to reach out. Otherwise, have a great rest of the day.